In this video, we're going to talk about specific heat. When you have a change in phase, it's inevitable that you are going to it's going to require some sort of energy. Either energy has to be put into the system or energy is a product of the system. Now, the heat of vaporization is the amount of heat or the amount of energy that is required to convert a liquid to a gas. Whereas the heat of fusion is the energy required to convert a solid into a liquid. So you'll notice if we go back to our slide, which shows water, there is this change in temperature, but once you get to 100 degrees Celsius, there is no change in water, but you keep adding heat. So in this state, or in this phase right here, there is going to be both water and steam. So that is when it starts boiling, and they're going to exist together at the same time. Now, we can also talk about the specific heat. And the specific heat has a very specific definition, if you will. And it is going to be the energy required to raise the temperature of 1 gram of substance by 1 degrees Celsius. And we can use this mathematical equation right here, Q equals ms delta T. Q is heat, and it will generally be given in units of joules. And that's because the specific heat is in units of joules. M is the mass, and it needs to be in units of grams. S is the specific heat, and it has units of joules per gram degrees Celsius. And then finally, delta T is the change in temperature. And that needs to be in degrees Celsius. Now, when you are calculating delta T, it is always going to be your final temperature minus your initial temperature. Here is a big table of the different specific heat values. You do not need to memorize it. You will always be given the specific heat values on a quiz. So let's get some practice using specific heat. So in this first example, it says how much heat is required to heat 35 grams of copper from 34 degrees Celsius to 100 degrees Celsius. So where it says how much heat, this tells me that I need to solve for Q. 35 grams, that is my M. And then I have delta T because I have a change in temperature. Whenever you're calculating specific heat, you're always going to have a change in temperature. And since this gives me the identity of the substance, well, I can use that to find the specific heat. So I can go back to my table and I can find copper, and here is the specific heat of copper. So I can take that over here. S is equal to 0.38 joules per gram degrees Celsius. So this is a plug and chug situation where we have Q is equal to ms delta T. And the problem gives me my mass, so I can plug that into my equation. We have 35.0 grams. And then I can multiply that by my specific heat, And then I can multiply that by my delta t. Now, you can either calculate the delta t prior to plugging it in, or you can just plug it in and calculate it as you go. But remember, delta t is equal to my final temperature minus my initial temperature. So that is going to give me my delta t. When we calculate that out, we get 66 degrees Celsius. So I can plug that value in right here. Notice that my grams cancel out, my units of degrees Celsius cancel out, and I'm left with units of joules, which is good because that is a unit of heat, and that is what it is, and that is what I'm trying to solve for. So go ahead and get your calculator out and plug this in. And I get 877.8 joules. You can also just record this as 878 joules. Either is fine. In this next example, notice we're given the amount of energy and we're asked to solve for the specific heat. So we have Q equals ms delta T, but in this problem, they're asking us to solve for Q. So, or sorry, it's to solve for S. So I can rearrange this to solve for S, and S is going to be equal to Q over M delta T. Now my Q is 3.5 times 10 to the 3 joules, and I can divide that by the mass, which is 25.3 grams. And then I can multiply it by my delta t. So my delta t is going to be 235 minus 25, which will give us 210 degrees Celsius. Now, when we plug that into our calculator, I get 0.659 joules per gram degrees Celsius. Now, since specific heat is specific to each substance, I can use this value to figure out what the identity of that metal object could be. So if I go back to my table here, I know it's not copper because copper has a specific heat that is much lower. So I can just kind of go through and reason my way through this. And keep in mind, this is a very limited table. I see that silica glass has the closest value, but is silica glass a metal? No, it's not. So it can't be that. So on this table, the closest value I would have would be aluminum, but that's pretty darn far away. So in order to identify this, I would need to look at a more substantial or a table that has more specific heat values of metals.